Let's continue with the other two more critical exponents, and there is, remember, the correlation function. This is, for example, magnetization density at R correlated with magnetization at 0 at the origin. This correlation function around in the vicinity of critical point goes like R to the minus P exponential minus R over L. L, the small l, is the correlation length which diverges at the critical point, and P is the power law decay. So for both of these quantities we have exponents, L diverging like T to the power minus nu, and power law decay depends on dimensionality of the system, D minus 2 plus eta. Eta is another critical exponent. So it is like R to the minus P, R to the minus D minus 2 plus eta. So it is an exponent in that sense, this quantity. So we have defined 4 plus 2, 6 critical exponents, but they are not all independent. Well, one more important thing about phase transitions is the scaling theory. Apart from these critical exponents, let me talk about that. Extremely important property. The fifth important point, scaling. Now, this concept involves dimensional analysis. Before I go into that, all these coefficients can be calculated for different models, isn't it? We can define a model for a system. Within that model, we can calculate these critical exponents. So they are not only defined like this, but they can be calculated by choosing a model to describe our system. Now, these exponents, as I told you, are not all independent. There are some relationships between them. And to introduce them, we have to look at the scaling theory, which is depending on the dimensional analysis and the fact that correlation length is the most important length. Correlation length L, small l, becomes of macroscopic magnitude, becomes macroscopic. This is important at critical point. So if the correlation length becomes macroscopic, all the other microscopic lengths are becoming unimportant then, isn't it? What is the meaning of microscopic lens becoming unimportant? Is that there's some universality in this phase transition. Many systems have a similar behavior because the microscopic landscapes becoming unimportant means it doesn't matter whether you are dealing with a spin system or an alloy system. Huh? So the microscopic details become unimportant. So this means microscopic details becomes unimportant. Not important. Close to the critical point, of course. This means universality. Okay? This causes universality. So scaling theory or scaling hypothesis is that close to the critical point, the anomalous parts part of a quantity, of all quantities, with dimension length will be proportional to correlation length to the power n. Okay? Extremely important. All dimensions will be proportional to the correlation length to the power n. So using this, you can get relationships between critical exponents. I will summarize them as follows. These relationships goes with the names discovered them. For example, gamma is nu 2 minus eta. This is Fisher law. Alpha plus 2 beta plus gamma is 2, which is Rushbrook law. Gamma is equal to beta delta minus 1, Vidal law. Nu times dimensionality is 2 minus alpha, Josephson law. These are all all experimentally verified. So the correlation length is the only length of importance in the vicinity of critical point, scaling hypotheses. All the other length scales of all other quantities scale like critical exponent to the power n, as I have written. So with these, we have to only calculate two independent critical exponents. That's enough to find others by using these relationships. Okay? So there are only two independent coefficients, enough to calculate the other four from these relationships. So we have all the 6 critical exponents available to us. Do you have any questions about this? Scaling, giving you a universality. Do you understand why it should be a universal thing? Phase transitions, there is some universality in phase transitions. Yeah? Because something funny is happening at the phase transition. There's long-range correlation. Think about ferromagnetism. Something happening here, but it all of a sudden expands and covers the whole crystal. All of the spins are in the same direction, isn't it? So there is a long-range correlation. Correlation length becomes very large, and microscopic quantity length of the crystal. Yeah? So what is happening at a local microscopic piece of the material is unimportant. If this is unimportant, then it is not important really whether you are studying spins or something else. They will have some universal characteristics. And the result is that the critical exponents are related. Only 2 independent critical exponents exist. There is some universality. Okay, now after these basics of the phase transitions, we can go into examples of first and second order phase transitions. What are the examples? Can we study a first order phase transition and a second order phase transition? A continuous and discontinuous phase transition. Yes, we can do that, and I will do this now. A first order phase transition, a discontinuous phase transition is a transition from gas to liquid. So gas, liquid, we can study. Why? Because we have studied the equation of state for an imperfect gas with interactions. And it was an equation of state known as van der Waals equation of state, isn't it? Which includes in it the effect of repulsion and attraction. Huh? So using that, we might model a first order phase transition. That's what I'm going to do now. After the basics of phase transitions, basic definitions, we can now go to an example. Gesundheit. A first order phase transition. We can study, we can have enough information to be used for this. First order phase transition. gas to liquid means we are studying condensation. And my starting point to understand this transition is the van der Waals equation of state. This must be capable of discovering the properties of this condensation. For a gas. Well, we can write that as P plus A over B squared V minus B NKBT, or write this as capital B or pressure is NKBT over V minus B minus A over B squared Well, let's look at the critical point for this gas. It is a PVT gas. When you look at P versus V, remember, it was a region like this. So, and the critical point must be something like this. So there is an inflection at that point. That's the critical point. I have shown this in my three-dimensional phase diagram. Remember that region, gas plus liquid region. So that's the region. Above this critical point and below, we have to study what happens inside the coexistence region by using this van der Waals equation of state. Well, let's continue with this van der Waals description. Let's calculate the free energy. Free energy from the, well, for the ideal case, ideal gas, it is P equals NKBT over the volume, isn't it? And this A and B terms are defining the effect of B is the repulsive part, A is describing the effect of attractive part of the interaction potential. So interaction between particles. The free energy, Helmholtz free energy is U minus Ts. So dF is du minus Tds minus sdt. So that when you put the first law in for du, you have minus p dv sdt plus mu dm. So the pressure is nothing but minus df dv, keeping t and n constant. We have done this, I don't know how many times in this course. So you can integrate df minus pdv. You can easily find the result of this. Ideal Helmholtz free energy. We can also call this A, as in your book, is minus nkBT, and then the volume, because P is inversely proportional to volume, dV over V gives you ln B. Very simple. Now, in Van der Waals case, this is modified, of course. Let's do that. Van der Waals pressures. Well, now we have an integral like this, nkBT over V minus B minus A over B squared dV well, that thing is going to come out to be minus nkBT ln V minus B minus A over V. You can use this ideal gas-free Helmholtz free energy by, you can rewrite that as F ideal minus N kBT ln 1 minus B over V minus A over V. Okay? Just a rewriting of your result. Now, you see that this gives the following thing. For the critical point. This is at t equals Tc, but when t becomes smaller than Tc, you have the following behavior. So instead of being constant, we have a strange behavior, but we can handle that, as I'm going to show you. Now let's find that critical point. Critical point is an inflection point. Do you know anything about inflection points? What happens there? First and second derivative of the quantity is 0 in an inflection point. That means del P, del V is 0 at constant T, and del squared P, del V squared at constant temperature is also 0. Inflection points means not only first derivative, but the second derivative is also 0. First derivative is 0 at maximum and minimum points of the function, isn't it? Here, both are 0. If we use this for the van der Waals, we get the following two equations. If we use this for the van der Waals, we have n kbt. Why don't you take derivatives and see v minus v squared is 2a over v cubed. This is the first equation you are going to get. If you take the first derivative, if you take the second derivative, you get the following, n kbt over v minus b cubed is 3a over v to the 4. This is the second equation from the second derivative. Take the derivatives and you are going to see. Well, you can relate this 1 and 2 to find, this gives you a b which is 3b. So that if you use this in number 1, gives you n kBTC at critical temperature. You get the following result, 8a divided by 27b. So you get the critical temperature in terms of parameters of your van der Waals equation, A and B. Eh? Very simple. Put first and second derivatives to 0. This gives you also the critical pressure, which is A over 27b squared. You can solve it. Now, for T greater than Tc, we have an ideal gas-like behavior because higher the temperature, classical is your gas. Well, you can call this critical volume if you like, at the critical point. That's what you have. At the critical point, you have an inflection developing. For temperatures lower than the critical temperature, we have a funny behavior, a bit strange behavior. We have something like this. What is strange about this? This is not an acceptable behavior. Can you tell me what is strange about this? Just take a look. It is strange that we have a portion like this, because at that point, dP, dV is positive, isn't it? We have a positive slope. Why it is strange to have a positive slope. Why is it strange? Very simple question. dP dV, well, you are increasing pressure, volume increases too. It is strange. When you increase pressure, volume should decrease, isn't it? Such a simple thing, you should tell me. So the real behavior should be something staying constant, isn't it? Let's discover that a little bit more, with a little bit more calculation. Let's see what happens, what should happen. This unstable thing is not acceptable. This is unstable. Let's correct that. Let's correct that behavior. We have to go from this behavior to that. Okay? See, in first order phase transitions like this, that should stay constant, because when you heat the system, increase the temperature, there must be latent heat. Some heat must go into the phase change, so that the gas turns into liquid. Because in this region, some droplets of liquid should appear in the gas. There's some coexistence. So you should keep the thing constant, but the system keeps it constant till it goes from gas to liquid on the other side. This is the liquid side, this is the gas side, remember. Okay, let's correct that. Let's see how we are going to correct that. But why the time is flying today? Huh? Something funny is happening. But at least we started the discussion. I think we are going to handle this case. Let me tell you what I'm going to do for the second order phase transition. What do you think is second order? This is simple PVT system, pressure, volume, temperature system, a gas going into liquid, a nice first order phase transition example, but the second order phase transition example will be the ferromagnetism, a gas of spins which are disordered at high temperatures, go into an ordered state, magnetized state. That will be our strong interaction case. This is kind of a weak interaction case, isn't it? So this is also an example of weak and later strong interaction cases for phase transitions.